Okay, so how do we go about looking at whether or not NF-kappa B is associated with PDGF's ability to cause changes in cells? Well, we go about it two different ways. This is kind of a typical study. You try to inhibit the activity with drugs, and you try to inhibit the activity genetically. So what kind of drug can you use for NF-kappa B? Well, acetylsalicylic acid, aspirin. Okay, the aspirin that you can buy. We actually got this from Perrigo. Are you guys familiar with Perrigo? Yeah, so they make generic drugs. So I had a person working at Perrigo, and I just bought a big pile. So it really literally is the aspirin you buy. So if you take this compound and you dribble it on the cells, right, what we're looking for is a reduction in this height up here. Right? And lo and behold, you put aspirin on here, right, and down it comes. Right? So it's a drug that inhibits NF-kappa. It does a lot of other things inside the cell. Besides that, you know, anytime you put a drug on a cell, you're doing multiple things, right? And that's why you get side effects. So, and all we want to do is show that that this was correlated with PDGF causing these cells to act like a tumor. So what we have here are some dishes, right? This purple haze that you see out here are actually cells that are stuck to the bottom of the dishes that we stain. So we put a little dye on there, okay? And so that's why you get this purple haze. Where these cells come together and they start to grow on top of each other, right? That is a symptom or a symptom of a cancer cell. Right? Cancer cells like to do that. Uncontrolled growth. Normal growth says, okay, I've met my neighbor, I stop. Cancer cells, I've met my neighbor, I don't care. I keep on going. Right? So these little black or dark purple spots that you see out here, that's where the cells have gotten the gene and they keep on growing. Okay? So what we're looking for is when we add the drug, as in this case, these spots disappear. Right? And so they did. Salicylic acid, yeah, it doesn't work quite as well. This is another anti-inflammatory. It doesn't react or control NF-kappa B, and it doesn't make any difference. So we've used a drug. Inhibits NF-kappa B, inhibits the way the cells behave, and then we finally did it genetically as well. So what we have up here are two different genes that we put in that interfere with NF-kappa B. So once again, what we're looking for is lack of spots. And I know this slide generally doesn't show up particularly well, and I apologize. The point is that these spots that we see with PDGF alone, right, kind of disappear when we inhibit it with one gene or if we inhibit it with another gene. So we've shown drug, and we've shown the gene having an effect. Kind of a standard way of people looking at or trying to approach that kind of subject, whether or not a gene is important in terms of cancer formation. I'd like to leave you with a couple other thoughts. One is whether or not it's the stem cells versus the progeny, and who is to blame. This is kind of more of a recent development. Remember when we looked at this slide, I told you down here that, you know, here are the stem cells, if you like, because they replenish all the other cells that are above here. If we take this population, right, that's sitting out here in this tumor, we can ask a similar question. Okay, we have a tumor mass out here. Is there a certain few cells within this mass that is actually actively dividing and giving rise to the mass? Or is it everybody that participates equally in this process? Right? So is it the stem cells, right, are the ones that we're really interested in attacking, or is it their progeny? Excuse me. Turns out, like in most cancers, there really isn't a simple answer. Right? For some cancers, such as melanoma, the answer is that no, it's everybody. Right? You can basically inject into an animal a vanishingly small number of cells and get a tumor. Right? Other types of tumors, such as brain cancers, glioblastomas, it's really a very small percentage of the population of tumor cells that give rise to the burden of the tumor. Complicates treatment, complicates diagnosis, complicates what you're going to do. So what about cancer and detection? How do you go about detecting cancers? Obviously, people are trying to find ways of not doing surgical procedures on this. Mammograms are an important aspect of that, obviously, for breast cancer. People are looking for specific proteins that cancers might be secreting into the stream that you can detect. People are looking, as I said before, metabolic markers, increased metabolism, increased glucose usage. It's a way of detecting cancer. And early is better, right? The rule of thumb in treating cancers is the earlier you find it, the more success you have. Right? Makes sense to me, right? The smaller the tumor, the less chance it has to have a lot of different mutations, right? The more reactive it's going to be to a particular, either it is to cut it out, whatever. Right? The question is, what cost do you do that? And that's kind of a public health issue that we face today. It came up a couple of years ago when people were saying, well, mammograms should not be performed on all women over the years of, 45, I believe it was. Right? It should only be performed on women that have a higher risk for breast cancer. Why is that? Well, you expose yourself to radiation. The probability that the women that don't have a higher risk are going to form or have breast cancer is so low that it's not worth their health cost. And then again, there's a monetary cost. Right? It's horrible to think about, but there are only so many healthcare dollars to pass around. That's not for me to decide. It's a public health issue. Last, I'd really like to thank you for having me come down here. Just a few people in my laboratory that have helped me over the years. And again, thank you. And if you have any questions, please ask.